In this video, we will be discussing frequency domain modeling using transfer functions. Transfer functions are used for mathematical modeling in the frequency domain. It is a mathematical modeling method which represents the system such that the input and output are distinct parts. Hence, transfer functions are defined as the ratio of the Laplace transform of the output of a system to the Laplace transform of the input of a system. In some instances, instead of representing the entire system as a transfer function, we would like to represent the interconnection of several subsystems, each having its own transfer function inside each block. The block functions are easily combined to obtain the overall system block diagram representation for analysis and design. A transfer function can be expressed as a numerator polynomial divided by a denominator polynomial. Transfer functions with high-order polynomials can be solved using partial fractional expansion via MATLAB rather than hand computation. We can use the control system toolbox in MATLAB to represent transfer functions of single input, single output systems in continuous or discrete time domains. In MATLAB, we can represent linear systems as transfer functions in four ways. In polynomial form, using the MATLAB transfer function command TF, in polynomial form using a rational expression in S, in the factorized zero-pole gain form using the MATLAB command ZPK, and in factorized form using a rational expression in S. We can also transform a linear time invariant system model from one form to another, for example, converting a linear time invariant system transfer function in polynomial form to factorized form using the MATLAB command TF to ZPK, and converting from factorized form to polynomial form using the MATLAB command ZPK to TF. Let's look at an example of how to create transfer functions in MATLAB using the system GS for each of the four methods discussed. In the first method, which is the polynomial form, the single input, single output transfer function is created using the numerator and denominator coefficients. The numerator and denominator are represented by row vectors in which the numerator and denominator polynomial coefficients are entered in descending powers of S. GS is formed using the MATLAB command TF. The variable G is called a linear time invariant object or a transfer function model object, which contains data for representing transfer functions in polynomial form. Alternatively, we can express the transfer function GS in polynomial form using the rational expression S method. To create a rational expression in S in polynomial form, we first create a transfer function model for the variable S. The statement S equals TF of S must precede the transfer function if we want to create a transfer function in polynomial form, equivalent to the previous transfer function object. The statement S equals TF of S must precede the transfer function if we want to create a transfer function in polynomial form equivalent to the previous transfer function object created by using the MATLAB command TF. Afterwards, you would type the transfer function as you would normally write it by specifying GS as a ratio polynomial in S. The third method is the factor form method. Using the factor form method, the transfer function is created by entering zero poles and gain of the system that you want to express. The variable G is formed using the MATLAB command ZPK, producing a zero-pole gain object G. You can also create a rational expression in S in factor form by creating a ZPK model for the variable S. Similar to the rational expression in S for the polynomial form, the statement ZPKS must precede the transfer function if we want to create a transfer function in factored form. Afterwards, you would type the transfer function as you would normally write it, specifying GS as a ratio polynomial in S. Transfer function numerator and denominator vectors can be converted between polynomial form containing the coefficients and factorized form containing the roots. To convert between polynomial and factorized form, the MATLAB commands TF to ZP and ZP to TF are used. Let's look at another MATLAB example of transforming one transfer function model to another. To convert from polynomial to factorized form, We enter the numerator and denominator of coefficients of g of s as row vectors and determine the zero pole and gain parameters by utilizing the MATLAB command tf to zp. Similarly, we can convert from factorized form to polynomial form by entering the roots of g of s, which are the zero poles and gains. Then by using the MATLAB command cp to tf, we can determine the numerator and denominator coefficients of g of s to be converted to polynomial form. Afterwards, we use the printsys command to print out the transfer function in polynomial form. In conclusion, we discussed an overview of transfer functions modeling in the frequency domain, creating transfer function in MATLAB using the control system toolbox, and converting from one form of transfer function to another. If you've enjoyed this video, please like, share, comment, and subscribe, and I'll see you in the next video.